So let's say this time we have A. Let's say A, it contains the sun, the moon, and the star. Is that okay? So what are the subsets of A? So what are the subsets of A? So empty set is a subset of A, right? Because we mentioned that empty set is a subset of any possible set. So a subset of A is just a set that takes some items from A and to include. So this is a subset of A. Is that okay? This is a subset of A. And what else? Moon is also a subset of A. Is that okay? And what else? Star is also a subset of A. Is that okay? And what else? Sun and moon. This is a subset of A, right? Sun and star. This is a subset of A, right? And then what? What else? You have the moon and the star. This is also a subset of A, right? And what else? Are there anything missing? Is there any other set that is also a subset of A? Oh, okay, very good. So if we take everything, it is still a subset of A. So this is 1 subset, 2 subset, 3, 4, 5, 6, 7, and 8. So we have these 8 subsets, right? If you put them together into a set, put them together. So put them together. Okay, put them together. So you separate them by a comma. I missed the brace here. A comma, a comma, here, a comma, and a comma. So this white set, okay, it contains 8 items, 8 elements. Each one of them is a subset. Then we call this the power set of A. Of this A. Is that okay? Okay, let me let me quickly ask you something. Okay, so there are 8 items when A is equal to something like this. Sun, moon, star. Okay. Let's change it a little bit. Let's say A this time contains the 3 integers, 1, 2, 3. Then you will have a different power set, right? Because so you have the empty set, you will have a subset that contains 1, a subset that contains 2, and so on and so forth. In that case, how many items or how many elements are there in the power set of this new A? 8, right? 8. Okay. Now let's say this time A contains 10 items. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 items. How many items are there in the power set of A? 2 to the power 10, am I correct? How do you get this very quickly? So this is 2 to the power 10, that's true. So how do we count the different, so the total number of subsets of a set A? How can we count? This is by rule of product, right? So each subset, for each subset, you need to decide whether the first item is selected or not, whether the second item is selected or not, whether the third item is selected or not, etc., etc. So if you have 10 items, there are going to be 2 to the power 10 ways of selecting a subset. And so that makes the size of this power set. So sometimes, okay, or what I like is, this is a shorthand notation. So this is a set, right? This is a set. And then with respect to A, and then I write the size, I denote this set as 2 to the power A. Is that okay? So it's like a power. And then this is something that helps me to remember the size, okay? because the size of this set is equal to 2 to the power the size of the original set A. Is that okay? Is that okay? Okay. And sometimes people will have a different notation. So sometimes people will use this power of A. So this POW, it represents power, okay? Or if you like, maybe just P of A. This is also okay. But this is what I like most. It has the best interpretation, okay, of the things here. Okay. And how about this? Okay. Okay, so how about another example? So let's say this time I have a set B. So what is B? B is the empty set. Empty set. B is the empty set. Then, what is the power set of B? So B is this one. So the power set of B is what? So it must contain something. Does it contain anything, or does it contain something? Is the power set of B empty or not? Okay, go back. Okay. So okay, go back to the definition. So I have a set B, right? Does B contain any subset? Is there any set which is a subset of B? Is there? The empty set. Remember, the empty set is always a subset of every other set, right? So the empty set is a subset of B. So B contains at least one set, the empty set. Okay? This is it. This is the power set of B. Of course, you don't like this. It is very confusing. You have open, open, close, close, right? So that's why we use this empty set notation to represent this. This looks nicer. Okay? Okay, this is okay. This is okay. But this is nicer. Okay. Okay. And then, okay. So we have got this introduction, and then something that is related. Okay. It's not the operation. It's about the size of a set. The size of a set counts the number of items inside. So if you have a set A, the size is denoted by, you write two things, the two bar enclosing this A. Okay? So you have A here, then the size of A here is what? Is 3. Is that okay? You have B here, the size of B is equal to 0. Okay? And then if you have 2 to the power A here, the size of this set, okay, the size of the power set of A will be equal to, as what we have discussed so far, the size of a power set is equal to 2 to the power the size of the original set. Is that okay? Okay? So that's it. So you have a new concept. But we can have size which is infinite. For instance, if we look at the set containing all the integers, the size is infinite. If you think of a set that contains all the real numbers, the size is also infinite. And then, okay, and then in the next class, not today, in the next class, we will talk about the two infinites are not the same. Okay, one is more infinite than the other. Okay, so they are real numbers, right? So there are infinite number of real numbers. There are integers. There are infinite number of integers. But then we will show that there are far more things of real numbers than integers. But on the other hand, okay, if you talk about integers and even integers, okay, so integers are, you contain all the 0, 1, 2, 3, 4 up to infinity or -1 and so on and so forth. And let's say not even integer, positive even numbers. Okay, so 2, 4, 6, 8, and so on and so forth. Both of them are infinite in size. But we will show that these two infinites are the same. So there are different classes of infinites. Some of the infinites are the same as the other infinites, and some of the infinite is more infinite than the others infinite. Okay, so we'll talk about this next time. Okay, so we have time, just perfect time to talk about identities. So what are identities? So identities are, so we have actually shown a particular identity there. A minus B is equal to A intersect the complement of B, right? And there are far more identities. Let me just write it down, and you will see that they are very similar to the logical equivalence we have studied so far. And they have actually the same name. Okay, so the first one is called identity law. Identity law. It says that for any set A, if you intersect the universe, it will always be equal to A. Right? You have A, and then you have so you have the universe color in yellow, and then you have A colored in red, and then you want to find out the intersection, the orange part. So the orange part will still be A. Is that okay? So intersecting with the universe does not have any effect. So it is like identity. Okay? And then union. If A union with the empty set, if I union with the empty set, then I still get the original set A. Okay? So the corresponding logical equivalence is like what? Okay, if you have a proposition P, if you AND true, then you get P. Is that okay? And then if you have a proposition P, if you OR false, then you still get the same proposition P. Okay? So if you understand this, then you understand this. They are actually the same. Okay. And then you have the second one. Second one is domination. Domination law. So domination law says A, this time we switch. Okay, if A intersect the empty set, then you will get empty. And then if you have A, but this time you union the universe, then you get the universe. Is that okay? And the corresponding logical equivalence is like what? If you have P, you AND false, then you get false. If you have a logical proposition P, if you OR true, then you get true. Is that okay? Okay? Is that okay? Everything here, you can prove it by using the Venn diagram. Okay, and then of course we will have more ways to prove them. We'll show how to prove identities later. But let me introduce the important identities first. The third one is idempotent. So what is idempotent? Idempotent is you apply yourself many times. So if you have A, and then you intersect A, then you get A. You have A colored in yellow, you have A colored in red, so the orange part is still A. A or A is still A. So similarly, if you look at it, so it is like P and P, you still get P, and then P or P, you still get P. Okay? Okay, and then we have also the complement law. So the complement law is, so let me write in this form, is you have an A, you get the complement. So this is the complement of A, right? This is another set. And now you have this set, and you make a complement of this. Then what will we get? Yeah, you get yourself. Is that okay? It's like A is the light bulb, you somehow switch off the light and then you switch it on. So if you do this 2 times, then you get A back. So the reason, so it's not the reason, but it is similar to if you have a proposition, you negate it, and then you further negate it again. So complement is like negation, then you get the original proposition P. Is that okay? And then commutative. So commutative is you can switch. So A intersect B is equal to B intersect A. So this is one law. And then you have A union B is equal to B union A. Okay? Notice that somehow we still need to write down this very simple law. It's not obvious that an operation, after you apply an operation, the ordering does not matter. So A union B must always be equal to B union A. So think about matrix multiplication. Okay, if you have 2 square matrix, 2 by 2, let's say 2 by 2 matrix, A multiplied with B will not be always the same as B multiplied with A. So this multiplication on what? On 2 by 2 matrix is not commutative. So it's not everything, every operation is commutative. But here, for this set operations of for the propositional, for the logical equivalence operation, then they are commutative. So we need to write it down. And then associative. So associative law is you have A intersect B intersect C. You do the first 2 first, and then you do this afterwards. It's the same as you do B, C first, and then intersect with A later. So the ordering of this does not matter. And because of this case, we can simply write down this as A intersect B intersect C. So if the symbol here are all the same, N. So you can do these 2 first, or you can do these 2 first. It doesn't matter. Okay, and we also have the or. So if A union B union C, it will be equal to A union B union C. Is that okay? And whenever we have associative law, we can omit the bracket. A union B union C. We can omit the bracket when we are doing a sequence of consecutive operations of the same kind. Okay, so this is associative law. Okay, so distributive law. So distributive law, you have A, you have AND, B or C. Okay, and the other one is A union B intersect C. So it is like A times B plus C. A times B plus C is equal to A times B plus A times C. So this is equal to A intersect B union A intersect C. And similarly, this also works for the opposite case. So this is going to be A union B intersect with A union C. Okay, so this is the distributive law. Okay, let me finish the laws. So the other one is the famous De Morgan's law. So De Morgan's law is to turn things upside down. Okay, if you have A and B, to turn things upside down, it becomes what? A, and then N becomes O. So intersect becomes union. This one, and then if you have A union B, then it will become what? It will become not A intersect not B. Is that okay? E. That one is called, so I make a mistake. This one is called complementation law, or perhaps called negation law. There's another law called complement law. So the 9 is called a complement law, or let's call it the version number 2. Complement again. So this says that if you have A, you intersect not A, what will you get? If you have A, you union not A, what will you get? What will we get? A intersect not A, what will we get? Empty, right? A union not A? Universe, yes, very good. Okay, there's one more law, so you can check this one. But De Morgan's law is very interesting. So just to remind you, what is the De Morgan's law, or how amazing it is, you can write down something like a very difficult proposition, like A intersects B, and then or A union C. Okay, something like this. So let's say I have a set that looks like this, and I want to negate it. Then what will it be? I want to make the complement of this. What will it be? So it will be equal to what? It will be equal to the complement of this A intersect B. Union becomes N, and this complement becomes A union C. Am I correct? And then we can actually do this further. This one goes inside. So not becomes not. So it looks like it becomes this one. Is that okay? And then for this one, what will happen? It will become A intersect C. Is that okay? So it is like you look things from left to right. Whenever you see open, you write down open. Whenever you see a set with a bar, you change it into the original set. If you see a set without a bar, you change it into a set with a bar. When you see a intersect, you change it to union. When you see a union, you change it to N. When you see a close, you close it. That's it. So it is super easy to use De Morgan's law to change one thing into its complement. Is that okay? Okay. So that's it. Okay.